So we begin. We start off with this thought question, and the question says this: is it possible for an object to have a constant speed, but also still be accelerating? Can you have a constant speed, yet also still be accelerating? Yes or no, and convince me. What do you think?
Yes.
Someone says yes. Who said yes? Convince me.
It could be going in circles.
Okay, so you've seen the punchline, or maybe you thought of this on your own. Because all vectors have both magnitude and what? Direction. You can have an acceleration, a changing velocity, if instead of changing the magnitude, which would be constant speed, you change the direction. And a great example of that is an object moving in a circle. So here's objects moving in a circle, and they're going roughly at a constant speed in that it's taking about the same amount of time to go around in the circle each time. I'm trying to go at a constant speed. But you can imagine if we had a computer controlling this, we could get this going at exactly a constant speed. So the answer is yes, you can go at a constant speed, yet still be accelerating. How? By changing direction, like moving in a circle. Did I hear a phone go off in my classroom? I thought I heard a phone beep in my classroom there. Whoever that is better get it on vibrate or silent, because we want our Timbits. So, for an object moving at a constant speed in a circle, and we're going to call that uniform circular motion, its velocity is changing because its direction is changing, although its speed is constant. It's okay, I play loud videos, so we'll get the music from next door for a short little clip there. And if its velocity, I know which one they're looking at. They're doing the firing the guns from the forces unit last year, the recoil on the guns, right? That's what that one is. So, back to here. Its velocity is changing since its direction is changing, and if its velocity is changing, here's the key. The object must be accelerating. This is the most important fact I want to drum into your brain. If you're moving in a circle, you're accelerating. If you're moving in a circle, you're accelerating. If you're moving in a circle, you're accelerating, and that leads to a couple of questions. The first question is this: if you're moving in a circle at a constant velocity, at a constant speed, what direction is that constant speed? So I'd like you to use your imagination as, again, I swing this around and around and around and around and around. If I stand facing Bree, okay? And if I were to freeze frame life when this mass and the rope were right here, pointing directly at Bree, and if I were to cut the string, who has to duck, Bree or Mark? What direction is the velocity when you're moving in a circle? If I cut the string right here, who's ducking, Bree or Mark? Mark is. When this mass is right here, it's traveling towards you guys. When the mass is right here, it's traveling towards your left. When the mass is right here, it's traveling towards the front of the room away from you. When the mass is right here, it's traveling to your right. And we have a fancy phrase for that. We have a fancy saying for that. We say, the direction of the velocity is tangent, let's even use quotation marks, tangent to the radius. It's perpendicular to the radius. If you want to get the direction of the velocity, it's at right angles to the radius. It's 90 degrees to the radius. And I can see I need to convince you. So hopefully with those videos I convince you that the direction of the velocity is 90 degrees to the radius. But then the next question is, what direction is the acceleration? I've told you there has to be an acceleration because you are changing direction. And to get it, we're going to do a vector subtraction. So I know that for constant acceleration, Vf equals Vi plus At, or A equals Vf minus Vi over t. Now, I got to be technical here. We're soon going to show that our acceleration is not constant, so we're going to do this over a very short time interval so the acceleration is nearly constant. And, Ryan, time, see it right there? Time, scalar or vector? Folks, time, scalar or vector? Scalar. So the direction for acceleration is going to come from this subtraction, not from the time. So what I'm going to do is I'm going to find what the direction of Vf minus Vi is, and that should tell me the direction of the acceleration. Because dividing by delta t won't change the direction. Dividing by a scalar can't change your direction. So we're going to subtract Vf minus Vi. How do we subtract two vectors? Ha! We don't. What do we do instead? Okay. So I'm going to write here, this is really going to be Vf plus negative Vi. And I've drawn a little picture here. So we have an object that's moving in a circle, and Vi is tangent to the radius, is right there. And then like a tenth of a second later, it's right here. There's V final in that direction. Still also tangent or perpendicular to the radius. So if I were to draw this, Vf looks like this, plus, which way is Vi? Well, that way, up and to the left. So which way is negative Vi? More specific. If Vi is up and left, which way is negative Vi? Down and right? I'm going to add these two together, tip to tail. It's going to look like this. Here's Vf. There is negative Vi. And you got to look close, but Riley, can you see the resultant is like that? The resultant, oh, that's a bad diagram. The resultant, do you know what direction the acceleration is? Toward the center. When you're moving in a circle, you're accelerating towards the center. Now that's a lovely vector mathematical proof, but I can give you a better proof, Joel, just based on your own physical experiences. I've talked to you already, and we've agreed that our bodies can detect acceleration. Our bodies have a built-in accelerometer, but it's backwards. Because when you step on the gas accelerating forwards, which way do you feel like you're getting pushed? Backwards. When you hit the brakes accelerating backwards, which way do you feel like you're getting pushed? Forwards. So, when you're in a car and you go around a corner really fast, which way do you feel like you're getting pushed? Outwards. So which way must you be accelerating? Inwards. 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 This is going to be the second key point. If you're moving in a circle, I can tell you the direction of the net acceleration. It's inwards. Oh, did I say acceleration? I can also then tell you the direction of the net force. It's inwards because F equals ma. So an object moving in a circle is accelerating towards the center, accelerating inwards. Example 3. A ball is on a frictionless tabletop and it's rolled along a circular track as seen below in a top view, so we're looking down at it. The track is not a complete circle. We've cut part of the circle away. So the ball rolls really fast. When it gets to the end of the track, what path will it follow? Path A, due to the fact that the ball has some circular momentum, which keeps it moving in a circular path for a while after it leaves the track. Path B, since when it leaves the track, there is no force from the track and the object should go in a straight line at a steady speed. Or path C, since when the track is no longer supplying a force on the ball will fly outwards the same way as you feel like you're getting pushed outwards when you go around the corner in a car. Path A, path B, or path C. You know what? Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. Don't make fun of me, Mr. Dueck. I'm going to vote, please. So you ready? Who says, path A, Mr. Dueck, it wants to keep going in a circle? 1. Who says, Dueck, path B, that's got like physics words in it? Lots. Who says, hey, path C, Mr. Dueck, I've been on a merry-go-round when I was a child, and when I let go of the merry-go-round, I thought I went flying outwards. No one. Why is B correct? Sorry, Sasha. Why is B correct? If you're moving in a circle, oh, go ahead, Seth.
Because when it left the circle, its velocity was towards that end, and since there's no track to keep it returning, it'll just continue in that direction.
Why? Once it leaves the track, are there any forces acting on it? Ah. So I think we can even bring in some good physics terminology. We can say, once it leaves the track, there are no forces, so Newton's first. Objects will continue in a straight line at a steady speed. By the way, when it's in the track, is it traveling in a straight line at a steady speed? No, it's changing direction. So that must mean that there must be a force acting on it while it's in the track. Okay. This concept is important because to the average non-physics layperson, because they've gone around the corner in a car, they believe that when they go around in a circle, there is a force pushing them outwards. So why is the turn the page. Why is the acceleration inwards? When I go around in a car, the push that I experience seems to be outwards. That is not a push. That's actually, Joel, Newton's first. Your body has mass, it has inertia, and so it wants to keep going in a straight line at a steady what? Speed, okay? It wants to keep doing that. Now the car is accelerating inwards. What does your body want to keep doing? Going in a straight line at a steady speed. Now that means for you to stay with the car, something has to apply a force to you. Part of it is friction between your bottom and the seat. That applies a force to your lower half. But your head and your torso are not attached to the seat very well. They want to keep going in a straight line at a steady speed. So what applies the force? I'd like you to imagine you're in the passenger seat right now of a car, and the car is making a quick left turn. What applies the force? You get a normal force from the door and the window. But because, again, you're not used to inanimate objects applying a force on you, you think it's because you're being pushed outwards. Because you're experiencing the forces come in pairs, you're experiencing the reactive force. Oh, the door pushes on you, so you push back on it, and you think, oh, I'm being pushed outwards. No, 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 no. You're being pushed inwards because your body wants to keep going in a straight line at a steady speed. Newton's first. It's inertia, not a force. And that's very, very, very important because years of experience lead most students to believe that there is an outwards force. And in fact, society gives it a name. I hear it all the time and I cringe. I hear people talking about centrifugal force. The reason I flew out of the car was centrifugal force. The reason I fell off the merry-go-round was centrifugal force. Then you put an F there. There is no such thing as centrifugal force. I'm simplifying. You can make an argument that there is, but for the purposes of Physics 11 and the way we're going to be drawing our free body diagrams, centrifugal force is a myth. It's inertia, not a force. It's your body or whatever mass you're looking at wanting to keep going in a straight line at a steady speed. Okay? In fact, they call them centrifuges. They're not using a force. They're taking advantage of inertia. They shouldn't be called centrifuges. There's a proper name for circular force, and we'll learn that next class. So what I want you to realize is that the outwards push, first of all, is not outwards, but it's in a straight line. And it's not a force, but merely inertia. Your grandfather may admit to this. He may be old enough. Back in the 1960s and the 1950s, before seatbelts were mandatory, back when cars were big and had bench seats on the front, not bucket seats, but bench seats. If you were a young teenage lad going out on a date, you would get some surfer's wax, and you would put surfer's wax all over the passenger seat, making it very slippery. And then what you would do is you would drive with your right hand on the back of the seat, and you would make a quick right turn. And your girl would come sliding right into you. Hi, honey.
You just made a
right turn. I'm doing a right turn. The physics is correct. Okay? If I make a quick right turn, the girl comes sliding, and that's not what's happened. The girl kept going in a straight line at a steady, but because I'd removed friction, the car rotated right underneath her and brought her into my field of path, and I could put my arm around her. Check with your granddad. See if he fesses up to that. He might. He might. We're just starting to reach the generation now where there's not as many. 5 and 10 years ago when I was teaching Physics 12, there were still grandparents who had grown up as teenagers with the bucket seats and before seat belts. Now, I don't know when were your grandparents born or when were they teenagers. If they weren't teenagers in the 1960s, if they were teenagers in the 1970s, that's when seat belt laws came in, and so they wouldn't have pulled that trick off. But it was a classic. Sorry, ladies, but it was a classic. Good physics. Good physics. Or the modern day equivalent is this. Example 4. If fighter pilots move too fast into a loop, they can become unconscious due to a lack of blood flow to the brain. The blood can flow to their feet. This is sometimes attributed to centrifugal force. It's not centrifugal force. What's really happening?
You're leaving your blood behind?
Jordan.
You're leaving your blood behind?
Because the blood wants to keep going in a straight line at a steady
Speed.
and you get pushed up by the seat. In fact, you know what? We can draw a little picture. We can draw. It's going to be a lousy picture because I can't draw. Okay? So, here's the pilot. And most of the pilot's blood, most of your blood, is in your torso. I'm just going to color it red like that. Okay? Ideally, most of your blood is pooled in your heart, in your torso, and in your brain, but I'll just focus on the stuff in your torso. So let's suppose the pilot does a sharp loop. The blood wants to keep going in a straight line at a steady speed. So if we get to this situation here, we have a situation where, right? Now we say, oh, the blood pooled in his feet. No, actually his brain and torso was forced away from his blood. And if you're not careful then, you can black out. So let's get to the actual calculations. How do we calculate circular acceleration? The proof is a little bit long, I have to be honest. It's about a one-page proof, and my little math nerd heart would love to walk you through it, but I'm just going to give it to you. Hey, what letter do we use for acceleration? What letter do we use for acceleration? A. So for circular acceleration, my symbol is an A with a little subscripted C for circular. And it's equal to V squared over R, where V is how fast you're traveling around the circle, and R is the radius of the circle. It's a scalar equation because the direction is towards the center. And it depends on where you are in the circle, what direction the center is. So I left off the vector symbols, even though acceleration is a vector. This gives you the scalar value. What's the direction? Towards the center. So show me the picture and I'll show you where the center is. Now, this leads to the next question, Mr. Dueck. You see, this velocity that I wrote here, you could also technically put a little c next to it. It's circular velocity. It's the speed that you're traveling in a circle. And so I guess the next question is, well, how do you figure out how fast you're traveling in a circle? I know how fast you're traveling in a straight line. How do you figure out how fast you're traveling in a circle? Well, we did say you're at a constant speed. There is an acceleration, but Matt, the acceleration is changing the direction, not the speed. So for a constant speed, speed is just distance over time. By the way, this equation here is on your formula sheet. The one I'm about to give you for circular velocity is not on your formula sheet. We okay there? Riley ducked out? We're going to pause here. So we were trying to derive the equation for circular speed, circular velocity. And so I said, well, speed is distance over time. This next equation, not on your formula sheet, and that's why I am showing you how to derive this one. Circular speed is going to be distance. The distance around a circle. What's the fancy word for the distance to go around the circle? I heard someone say it. What? Circumference. Now, what's the equation for circumference? Which is on your formula sheet if you blank out, but 2 pi r over how much time? Well, there's a fancy word for how long it takes to go around once. We call it the period, and we use a capital T for period. V equals 2 pi r over t. Circular speed is 2 pi r over t. You want to know how fast you're traveling in a circle? If you know the radius, time how long it takes to go around once, and that tells you what your tangent to the radius speed is. By the way, a concept closely related to period is the frequency. We define frequency as the number of cycles per second. So period is how many seconds for one cycle. Frequency is how many cycles for 1 second. They're reciprocals of each other. Frequency is measured in hertz, symbol Hz. And the period is 1 over the frequency. Also, the frequency is 1 over the period. Bree, what I'm saying is if you know one, you know the other one. If you know the other one. So sometimes in a question, if they're talking about circular velocity, sometimes they'll tell you the period, how long to go around once in seconds. Sometimes they'll tell you the frequency in hertz. Okay, then take the reciprocal, and that'll tell you how long to go around once in seconds, and you can do that. So let's start to apply some of this stuff. Example 6. An object is moving at 4 meters per second in uniform circular motion. It accelerates at 2 meters per second squared for 3 seconds. Find A, the final speed of the object. This is a trick question, Callum. What phrase did I underline? In uniform circular motion, you're moving at a constant speed. There is an acceleration of 2 meters per second squared, but what that acceleration is changing is not the speed, it's changing the direction. So when it says find the final speed of the object, you know what? It's still 4 meters per second. Why? Because if you're moving in a circle in uniform circular motion, by definition, Sasha, your speed's not changing. That's one that bugs kids, because they all want to go VF equals VI plus AT. They all want to go 4 plus 2 times 3. No. But there's an acceleration, Mr. Dueck. Yeah, but that acceleration is changing direction, not speed. Oh, and the distance traveled? Wait a minute, Mr. Dueck, isn't it plus a half AT squared? There's an A, Mr. Dueck, isn't it plus a half AT? No, because that acceleration is not changing your velocity. What's that acceleration changing? Direction. You're traveling at a constant speed, and for a constant speed, distance is VT. It's 4 times 3. The distance you would travel is 12 meters. Why'd they give us that 2, Mr. Dueck? Well, because there is an acceleration. It's just changing the direction. And the reason I know to do this is because of the phrase that they underlined. They told me I'm moving in a circle, different rules, uniform circular motion. There's a second equation for circular acceleration. We already said that circular acceleration, Jordan, was v squared over r. And I said that circular speed is 2 pi r over t. You know what? What if I put that right into there? I'll get this. 2 pi r over the period squared over r. That's v squared over r. Isn't it? Same equation, I just did a substitution. But we can clear some brackets. Because this is going to be squared, 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 and squared. So what's 2 squared? In your head, please. What's 2 squared? What's pi squared? Just pi squared. What's r squared? Just r squared. Over. What's capital T squared? Capital T squared. And that was all divided by r. Bree, that's just the same as putting an extra r down there with the t. Oh! How many r's on top? 2. How many on the bottom? You know what? One of the r's can cancel. And this gives me my second equation for circular motion. This one is on your formula sheet. Another way to calculate circular acceleration is 4 pi squared r over t squared. Which one's correct? Well, they both are. It is pretty obvious which one you're going to use when. Roy, if they give me the speed, I'll use v squared over r. If they tell me how long it took to go around, I'll use 4 pi squared r over t squared. It's that obvious. They're going to give you the radius no matter what. Okay. Also a scalar equation. What's the direction? Towards the center. So we have AC equals v squared over r, and it also equals 4 pi squared r over t squared, where t is the period, how long to go around once, r is the radius, and v is the circular speed. Oh, and that is distance, circumference, divided by time, period. The equations in the box on your sheet, the equation saying outside the box for speed, circular speed, not on your sheet, but hopefully I showed you how you can derive it in a pinch. It's distance over time, but think circular. So in uniform circular motion, we have a strange situation. The object is moving at a constant speed, but it's also accelerating. And this is because the acceleration is changing the direction, not the speed.
Can you go up further? Half a second.
Okay. So we have constant speed, but the acceleration is affecting the direction, not the speed. Oh, and the acceleration vector is changing because it's always inward, so depending on where you are in the circle, inwards is in a different direction. Always inwards, though. This means we can't use our constant acceleration equations. We can't use these. We have to use the equations for uniform circular kinematics. AC equals v squared over r, or 4 pi squared r over t squared. V equals 2 pi r over t. Distance equals vt. What's your homework? So number 1 says, for the Earth rotating on its axis, consult your data sheet to find the radius and period. On your formula sheet, on the front of it, you will find the radius of orbit and the period of rotation and the period of orbit for the Sun, the Moon, and the Earth. And we're going to start to use those an awful lot during this unit. You don't need to memorize them. They're on your formulas sheet. So you can, I think, do number 1. I think you can do number 2, number 3, number 4. 5 is good. I think I skipped 6. 7 is good. 8 is good and 9 is good. Skip 6, skip 10. However, I've got to show you some